Bonjour. All right, so back at it. Starting with number 11. Which of these is a correct description of the italicized term? So, factor is a response variable? No. Response variable is response variable. Factor is something you're manipulating. Replication means the experiment should be repeated several times, potentially. Levels are the same as treatments. No, levels are like the amount of treatment. Like if you're testing, does 5 milligrams have a different effect than 10 milligrams, than 20 milligrams, right? Because sometimes you're looking for an effective dose. So no. The response variable is the variable directly controlled by the researchers. No, that would be the explanatory variable, right? That might be the one you manipulate. The response is what happens, right? We don't control what happens. Otherwise, we're not doing real science. All right, B, vocab, yay, one down. More to go. 12. A department store has a promotion in which it hands out a scratch card at the checkout register. I don't know why I circled that. That's not actually important. With a percentage discount concealed by an opaque covering. The customer scratches off the covering and reveals the amount of the discount. The table below shows the probability that a randomly selected card contains each percent discount. What is the expected value of the percentage of discount? Okay, expected value. So I'm going to do this by hand this time. You can put this in your list just as a review of that. The percent can be in list 1. Probabilities can be in list 2. Remember that stat edit. Make sure you clear everything else out. Then you're going to go to stat calc, and you're going to do one variable stats. Your list is going to be list 1, and your frequency list is going to be list 2. So your probability can be your frequency list. This one only has 5 items, so I'm just going to do it by hand. I'm going to take the probability and multiply it by the percentage discount. I'm just going to leave the percents as whole numbers. And then I'm going to add that to the probability of getting a 10% discount multiplied by 10, probability of getting a 15% discount multiplied by 15, and the probability of getting a 25% discount by 25, and as you guessed it, probability of getting a 50% discount multiplied by 50. That would be awesome to get a 50% discount right now, especially on groceries. Honestly, I'd almost rather that than like a department store. I just want all the cheese. And plus 0.1 times 25. So this is me mumbling while I type it into my calculator. And bam, that all adds up to 12. So we are expecting a 12% discount. You should get the same mean. So what you're looking for here, if you do it in your lists, is the mean. Mean, expected value, same diff. Onward. Okay, good. Okay. In basketball, an offensive rebound occurs when a player shoots and misses, and a player from the same team recovers the ball. I have no idea if that's correct. There are 176 players on the roster for one season of professional men's basketball. The third quartile for the total number of offensive rebounds for one season was 143. So third quartile means that 75% is below and 25% is above. If 5 players are selected at random with replacement, that's important so we're not changing the probabilities from that season, what is the approximate probability that at least 3 of them, so 3 of 5, had more than 143 rebounds that season? Okay. So The probability in this distribution of having more than 143 rebounds is 25%. So the probability is 25%. We are looking for at least 3 of 5. So in 5, we want 3 successes. Is this looking a little binomial to you? It's looking a little binomial to me. All right, so because it's an at least, that's to the right, that's to more. So we're going to do 1 minus binomial CDF, because at least means 3 works, 4 works, 5 works. So we want all of them. So second vars, binom, CDF. The number of trials is 5. The p-value is 0.25. And we don't want to take out 3 because 3 out of 5 works, at least 3. So what we don't want to include is 0 gets more than 143 rebounds, 1 or 2. So what we want to take out is 2 and below so that we're left with 3 and above. Paste that. Bloop, 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 bloop. And we get about 0.104. So about 10%. 10% chance that if we took 5 players, at least 3 of them would have scored or would have had more than 143 rebounds. Blink. Okay. 14. A new smartwatch is manufactured in one part of a factory, then secured for shipping in another independent part of the factory. The weight of the smartwatch has a mean of 62 grams and a standard deviation of 1 gram. The weight of the packaging, all the stuff, has a mean of 456 grams and a standard deviation of 6 grams. Together, the distribution of the weight of the smartwatch and its packaging would have the following mean and standard deviation. Okay, so together, we're combining. This is addition. So for the means, we're going to add them. Means we're just going to add. So that would be 62 plus 456. Right away, looking at my answer choices for the means, and we're going to do this in parts. It's got to be bigger than 456, so these guys are out. Cool. When you are combining standard deviation, and this is true whether you are adding the means or subtracting the means, you're always going to combine standard deviation with the Pythagorean theorem of statistics. So we're going to take the square root of the standard deviation of 1 squared plus the standard deviation of the other, where is it? Squared. So we can't just add the standard deviations because remember they can deviate in opposite directions or the same direction. So there's more variability than just adding them together. So 1 squared plus 6 squared is 37. Square root of 37 is a little over 6. All right. That's it. You definitely need to remember, you always add inside that root symbol for standard deviation. Always, always, always. Even if this is being subtracted, you're always adding this. Cool. 15. The total cholesterol level in a large population of people is strongly skewed right, with a mean of 210 milligrams per deciliter. I think that's what that is. And a standard deviation of 15 milligrams. If random samples of size 16 are repeatedly drawn from this population, which of the following appropriately describes the sampling distributions? Okay. Some key things. The sample size is less than 30, which means if the sample size is less than 30, the sampling distribution will approximately match the population. The closer it gets to 30, closer that sample size gets to 30, the more normal the sampling distribution becomes. The further from 30, the more whatever the original population, the sampling distribution will be. So the shape is unknown? No. The shape is somewhat skewed right. So it was skewed right. We're going to stay skewed right. That sounds good. With a mean of 210 and a standard deviation of 3.75. Okay, so we'll talk about the standard deviation in a second. So somewhat skewed right. The population is strongly skewed right. Our sample size is halfway-ish to 30, so it's somewhat skewed right. That seems good. The shape is approximately normal? No, that's not going to be true because our sample size is not big enough to get us an approximately normal distribution. Takes out D as well. And then the skew is not going to switch. It's either going to stay skewed right or it's going to get towards normal as the sample size increases. So that one's out. So just by dint of process of elimination, everything but B is out. Now, why is this standard deviation smaller? I'm so glad you asked. Because our sample is 16, right? Our sample size is 16. Our standard deviation was 15 for 1. We need to divide that by the square root of the sample size, by the square root of n, which in this case is 16. So 15 over 4 is 3.75. That's where that comes from. This was a big point of, big spot for lost points on your final last fall. Cool. Good. DAC 16. In one metropolitan region, technical writers have an annual salary that is approximately normally distributed with a mean of 55,800. The first quartile of salaries is 48,815. What is the standard deviation? Okay, we're going to do this in a few steps. First quartile. That means 25% is below, which means we have an area and we don't have our standard deviation, but we can find a z-score for that. So what we're going to do is say inverse norm, because it's approximately normally distributed. And we're going to say the area is 0.25. The mean, we're going to leave at 0. And the standard deviation, we're going to leave at 1. We're getting our standardized test statistic. We are producing a z-score. If you leave this as 0 and 1, you're producing a z-score. Always label. And we get a z-score of about negative 0.674. So this is our z-score right here. The wrong stuff. Okay. Now, a z-score is actual minus mean over standard deviation. Well, we know our z-score is negative 0.674. We know our actual is 48,815. We know our mean is 55,800. And our standard deviation is what we're looking for. So then we ask the algebra fairies to grace us with their presence. And this and that switch, right? We're going to multiply both sides by our s, by our variable. We're going to divide both sides by this negative 0.674. And we end up with this equals, absolutely going to cheat this a little bit. And like, the sound effects are really important. I got to tell you. And blank. So we're going to end up with that. When we pop that in, 48,815 minus 55,800, and we divide that by that z-score we got, we get about 10,000 bucks. About 10,356. Okay, there we go. Now, the multiple choice wizard in me is looking at these answer choices and saying, all right, there's a bunch all over the place. These two are super close. It's probably one of those because they're so close. Still good to know how to get there, but if you were guessing, if you were like, I don't know how to do this, look at those answer choices and say, huh, there's got to be a reason those are both there. Maybe it's to trick you, but if you're just guessing, you know, can't be any worse than 1 in 5 shot. There you go. All right. 17, getting there. I think 3 more multiple choice. Okay, so a local library has a scanner to detect library materials that have not been checked out. Each item has a chip somewhere inside. Upon checkout, the chip is deactivated, so the scanner has a 98% chance of detecting an active chip, meaning the material has not been checked out, and setting off the alarm. The scanner also has a 3% chance of sounding the alarm when someone passes through without an active chip. It is estimated that 0.5% of library customers actually try to leave the library with an active chip. What is the probability that if the alarm sounds, this is going to be our denominator? The patron leaving the library has an item with an active chip. All right. If you're thinking this sounds like a probability tree, so excellent. If you hate the sound of the word probability tree, time to get over that. They're super useful. Let's practice. So there 0.5%, half of the library customers actually try to leave the library with an active chip. So we've got our thieves. Wow, I'm spelling wrong. Am I? Oh boy. It's one of those things. Now it's stuck in my brain. Thieves. Yeah, thieves. Okay, so that's 0.005. That's 0.5% chance of it happening, which means our goodies, our upstanding citizens, there is a 1 minus 0.005. It's too late for my brain. 0.995% chance, or no, 0.995 chance that the person is not trying to leave with an active chip. Okay. The chip is deactivated when someone checks out, so the scanner has a 98% chance of detecting an active chip. So, meaning the material has not been checked out and setting off the alarm. So, try to leave the library with an active chip. And upstanding citizens not leaving with an active chip. I may have set this up a little backwards. That's okay. 3% chance of sounding the alarm. Oh, no, we're good. 3% chance of sounding the alarm when someone passes through without an active chip. So these upstanding citizens, there's a 3% chance that the alarm sounds and a 97% chance that there's no alarm. For a thief, there's a 98% chance the alarm sounds if they're trying to steal the book. And that means there's a 2% chance that they'll get away with it. So what is the probability that if the alarm sounds? Okay, if the alarm sounds, that happens in this case and in this case. So we need to figure the sum of those probabilities out first. We're going to multiply through to get that. We're going to multiply through to get that, and then we add them together. So thieves was 0.005 times 0.98 plus, so that's this bit, 0.995. Most people are not trying to steal a book, and they only have a 3% chance of setting off the alarm. So altogether, times 0.98 plus 0.995 times 0.03. Well, now I really want bubble tea. I don't know why. So that gives us a 0.03475 chance that the alarm will sound, period. If the alarm sounds, the patron leaving the library has an item with an active chip, so that we actually have this situation. Someone is trying to leave without an active chip. So we're going to take the 0.005 times 0.98. So that's 0.0049. That's the probability that someone is leaving the library with an active chip and the alarm sounded, out of the total probability that the alarm sounds. Why did I grab that? That's about 14% chance. So even though this machine is pretty good, 76% of the time, 75.9% of the time, the alarm sounds, it's an accident. Only, 76. What am I talking about? 86. Only 14% of the time is the alarm sounding when someone's actually trying to steal a book from the library. Who would do such a thing? Okay. So again, you set up your probability tree. People are either thieves or not. And then based on whether that chip is activated, the machine has different probabilities of going off. So that's why I did the different probabilities of sounding second, because those probabilities depend on what's happening here. Cool. All right. 18. Which of the following is the best description of the power of a significance test? Probability that the null hypothesis is true. We never know. Type 1 error? No. Type 2 error? No. And actually going back, the probability of getting a type 1 error is equal to the significance level. The probability of getting a type 2 error is 1 minus the power. The probability of getting a test statistic at least as extreme as the actual test statistic if the null hypothesis is true, that's what the p-value is. What temperature change? Weird. So none of these are true, but they have meaning. The probability of correctly rejecting the null hypothesis, this is power. The power of the test is how likely are we to correctly reject the null, to have found something interesting and know that we found something interesting. All right, last multiple choice. A producer of skincare products has created a new formula for its cream to cure acne. To compare the effectiveness of the new cream to that of the old cream, the company conducted a double-blind randomized experiment. Volunteers with acne tried the old formula on one side of their face and the new formula on the other. So take note, one side of their face, other side of their face. So these are very, very tiny blocks, also known as matched pairs. When it's really, really small blocks so that each person is doing, one thing on one side, the other on the other, you're testing someone against themselves, that's a matched pairs. Which side got which formula was determined randomly. Good. Super good study design. The response variable was the difference in the number of pimples. Old formula minus new formula. Which is the correct significance test to perform? Okay, so I've already sort of given this away. You wouldn't do a proportion because you're not doing a proportion of pimples. We will talk next week about chi-square tests, but we have not done so yet. Those are also about categorical variables. So they would sort of fall in the same realm as proportions. They're just like fancier proportions. So then a 2-sample t-test but it's not a terrible answer here, right? Because we've got two samples, but matched pairs is better because these are not independent, right? One person isn't independent of themselves. And the reason you would do a matched pair is everyone has so many different things going on. You want to see both formulas on the same skin and lifestyle and all that stuff. So when someone is being compared to themselves, they wear one glove on the left hand, one glove on the right hand, one boot on the left foot, one boot on the right foot. That's a matched pairs experiment. There we go. Multiple choice. You did it. You get a cat as a reward. This is a new cat because my parents' cat is staying with us. His name is Bernoulli, like the Bernoulli trials for a binomial situation. Bernoulli trials are anything where the outcomes are either yes or no. Makes sense. He's a black and white cat. Bernoulli outcomes, he black and white, yes or no. He hates everything except for my mom. He loves my mom. I can't believe he meowed. He's usually pretty silent. Look into the camera, Boogie. Yes, you're a nice boy. You hate this, don't you? I wonder if he's gonna yell at me. You gonna hiss or you gonna scratch my face? I'm a little nervous. You're gonna scratch my face. You're being pretty good. You're so weird. Oh, there's the growl. Okay. All right. I hope that was helpful. See you soon for FRQs. Bye.